When what we want to do is attenuate both nitrogen and phosphorus. Both nitrogen and phosphorus is important for the downstream waters. So we want to remove as much as possible nitrogen and phosphorus from the urban waters. The optimal chemical conditions for removal of nitrogen and phosphorus are different. And so we rarely can do it all in one step. What we normally do is try first to remove phosphorus. Also, phosphorus is sometimes attached to particulates. So we want to remove phosphorus, and that occurs typically in oxygenated aerobic environments. And also the media is usually quite good at capturing phosphorus, at absorbing phosphorus. So there's two ways you can look at nutrients coming in and out of a system. You can look at the concentration. Is there a reduction in the concentration going out versus coming in? You can also look at the load of nutrients. So that's the concentration times the flow. So that's the mass of nutrients coming in, kilograms of nutrients coming in per day, for example, compared to kilograms of nutrients going out. And what we really want to have is less kilograms of nitrogen and phosphorus going out than kilograms coming in. And that means that there has been a retention of massive nutrients in the system, and usually that will be within the media. So these systems have special soils, particular media underneath the plants, and that media has been selected to absorb the nutrients quite well. And so it's always going to be a balance between the flow, how fast it infiltrates through the media, versus the ability of that media, that soil, to absorb nutrients as the water goes through it. So for nitrogen, the water moves into the subsurface environment. When it moves underground, there's a gradual reduction in the amount of oxygen that's in that water. The organic matter in the soil consumes oxygen as it decomposes in the soil. And so the oxygen concentration goes down, and as the water becomes anoxic, it moves into a type of chemical condition that is very conducive to removing nitrogen. We hopefully move into something called denitrification, which is a process where nitrogen that's contained in the water gets used by microbes, and then the microbes release nitrogen out of the system, so into the atmosphere. So that's the denitrification. So we're trying to create, in these rain gardens and also in the biofiltration systems, we want to create chemical conditions that remove the nitrogen. So we might use a filtration through a media, even if it's oxygenated. We might use that step to remove phosphorus. Further along, we might have another system like a biofiltration system that is focusing on reducing oxygen, creating an anaerobic environment, and that will remove the nitrogen. So you might have alternating systems. One system removes phosphorus, one system removes nitrogen, then you go back to a phosphorus removing system, and then you go back to a nitrogen removing system. And as you alternate, you're slowly bringing down both types of nutrients as you move through. It's what we call a treatment train approach. We found that these little rain gardens, even though they look really small, actually attenuated both flows and nutrients, but particularly nutrients, both nitrogen and phosphorus. They actually attenuated them really well.